Welcome to Chapter 2 of our Medical Statistics course. Today we're moving from theory to practical application, or how to make sense of the data we collect. This chapter is fundamental because before we can analyze data statistically, we need to understand what type of data we have and how to describe it appropriately. So think of this as learning the language of data. Just as a doctor needs to know medical terminology, we need to know statistical terminology. These objectives cover the essential skills for handling medical data. Notice we're not just learning calculation, but using and understanding different approaches. The key is matching the right summary method to your data type and research question. We'll use real examples from a foot corn treatment study throughout this chapter. Just as a farmer needs to sort different crops appropriately, you wouldn't store apples the same way as wheat. Statisticians need to classify data appropriately because different data types requires different analytical approaches. So if you're looking at nominal data, these categories are mutually exclusive. There's no order. So the examples would be like gender, it's male and female, blood group, AB, ABO, or marital status, or even a treatment center name. In ordinal, the categories are mutually exclusive and ordered. So we're looking at maybe disease stages, stage 1, 2, 3, or 4 cancer. Pain severity, mild, moderate, severe, and education level. On counts, this is the number of pregnancies, days in the hospital, it's integer values, it's numbers of medication, so sick days, anything that's just a count, this is what we're looking at. What about continuous? Continuous is measured. There's any value in a range of values. So example, your weight, your height, your blood pressure, your temperature. We could also do the age in years, hours, or minutes. And this is a critical point. The classification isn't just academic. It determines which statistical test you can use and how you should summarize the data and what graphs are appropriate. This real-world study gives us concrete examples of each data type. Notice how the researchers present different types of data differently. Percentages for gender, categories for smoking, and means with standard deviations for continuous variables, like age. This isn't random, it follows the principles we're learning today. So this is from Farden et al. In 2013, a real randomized control trial with 202 patients who have foot corns, calluses that cause pain when walking. 2 treatments were compared, a scalpel debridement and a salicylic acid plaster. Now, the scalpel debridement is the traditional way of treating a foot corn. This is a perfect example because it contains all data types that we are discussing. We're looking at gender, a nominal. Look, 42% male, 58% female in overall samples. Look how the percentages are reported. So this is standard practice. Our categories are mutually exclusive. There's no natural order. And then we have our smoking status, ordinal. We have 3 categories, non-smoker, previous, and current. This is a logical progression in smoking exposure. So you could argue current smoker has more recent exposure than a previous smoker. The number of corns. So this is a count. This is an integer value of 1, 2, or 3 corns per patient. Theoretically, you could have 0, but in this study, we're looking at people who only have corns, not someone who could theoretically have a corn. These are discrete values. You can't have 2.3 corns or 2.5 corns. Look at our age. It's continuous. If the mean is 58.5 years and the standard deviation is 15.6 years, it could theoretically be any value within biological limits. Now, the mean and the standard deviation are both reported. Look how they are reported. On corn size, we're looking at continuous data. So a mean is 3.9 millimeters. The standard deviation is 1.7 millimeters. So it's measured to the nearest millimeter, but it's theoretically continuous. So let's look at what are categories and how can we make sense of it, as well as how do we summarize the data. So let's look at the binary data to begin. This is the simplest case. It's just 2 categories. There's simple counts and proportions or percentages. Now, here's the thing. Let's look at this. It's the gender example that we have, all right? 42 males out of 101 total equals 42%. 59 females is 58%. So we always report both a count as an N and a percentage with the percentage mark. Percentages should always add to 100 and allow for rounding. Now let's look at multiple categories. So the treatment center data from table 2.2 in your textbook is what you can refer to. There are seven different centers ranging from 3% with Darnall to 54.5% central. Look how the table shows frequency and percentage. This is standard. There's the cross-tabulation concept. Table 2.3 shows treatment center by randomized group. Well, this is called a contingency table. It allows us to see if the randomization worked. Similar numbers in each group at the center. Critical for understanding is whether the groups are comparable. So now, can we compare them? Are they comparable? Are they similar? We're trying to make sure, are the groups similar or comparable? Are they made up of the same numbers in gender, the same race, same ethnicity, same job status? It could be anything. This is something you'll want to really figure out when you have groups. What about the binary outcomes? Well, in medical research, we often label outcomes as event or non-event. So that would be healed, not healed, death, survived, improved, not improved. Now, the choice of which is the event affects also how you present your results. Notice in this chart that Central treats about 55% of all patients. So this immediately tells us something important about a study design. There are gaps between the bars which emphasize these as separate, distinct categories. The height of the bars makes comparison easy. It's much easier than comparing numbers in a table. Also, the y-axis shows a percentage or count, and the x-axis shows categories. When using a bar chart, the bars should be the same width. Order also matters. We usually arrange from a highest to a lowest unless there is a natural order that exists. We should use bar charts when we're comparing categories, when we want to emphasize differences between groups. Bar charts are much better than pie charts for multiple categories. As our textbook says, bar charts display counts in mutually exclusive categories, and so the bars have spaces between them. Histograms show the distribution of a continuous variable, and so they should not have spaces between the bars. Let's look at the pie charts. These show the same data as the bar chart, but notice how much more difficult it is to compare categories. So can you easily tell if Jonathan Thorpe 12% is better than Limbrick 5%? It's much easier with a bar chart. Pie charts work with simple data and few categories, usually less than 5. So when you want to emphasize parts of the whole, then a bar chart is appropriate. When precise comparisons are not critical is also a way to use pie charts. You should avoid pie charts with data that has more than 5 categories and when you need precise comparisons. Also, avoid 3D pie charts. They really distort your perception. In considering our textbook and discussing pie charts, the textbook says generally pie charts are to be avoided as they can be difficult to interpret, particularly when the number of categories is greater than 5. So when looking at our mean, median, and mode, these are the 3 M's and the measures of central tendency. So we all understand, quote, average, but there are these 3 different types of middle. And so each one of them tells us something different about our data. When we're considering the mean, that's the arithmetic average. That is a formula. It's the sum of all the values divided by the number of observations. The strength is that this uses all data points. It's statistically efficient. There is a weakness, however. It is sensitive to outliers. So if you look at our textbook, we have an example where the corn size mean equals 3.62 millimeters, calculated from 16 patients. What this means is the median, the middle value, when the data is arranged in order, we could do that. But the strength is not affected by outliers. So that is really a great way of doing it on the median. Then the problem is it doesn't use all the information. It simply looks at everything in an ordered fashion. So if we look at the example in the text for 16 corn sizes, and they are ordered into 1, 2, 2, 2, 2, 2, 3, 3, 3, 3, 4, 4, 5, 6, 6, 10. The median is a 3 plus a 3 divided by 2, which is 3 millimeters. Well, the mode is the most frequently occurring value. And what that does, if we look at this in the example in the corn data, 5 patients had a corn size of 2 millimeters, and that was the most frequent. However, if you look also, it's useful for categorical data, like the most common blood type, the most frequent diagnosis. And one of the key insights for the corn data, with the mean at 3.6 millimeters times the median, 3 millimeters, suggests the distribution is slightly right skewed to the outlier of 10 millimeters. So viewing our measures of variability, we talk about how spread out is our data. So if we're looking at our range, this is a minimum to a maximum value. It's very simplistic. It's like where the data start and where the data end. So it's simple, but it's affected by the outliers. And so, what we look at is there is a formula, that is there's no formula in the range. It's what you're doing is you're just simply using two data points, the beginning and the end, the minimum and the maximum. So if you're using a corn example of 10 millimeters minus 1 millimeter, that means the range is what? 9 millimeters. So it only uses two data points. It's completely determined by outliers. Now, this is really good to use if you're just looking at a quick sense of spread. People understand range. What they struggle with sometimes is standard deviation, which is the average distance from the mean. Now, you have your, it uses all the data points. That to me is one of the great ideas. We're using the data point and we're using the same units as the original data. We're talking about what is the average distance from the mean. Now this we're using the sample mean instead of a true population mean. So this does create a slight bias that n minus 1 corrects. We call this degrees of freedom. We will lose 1 degree of freedom by estimating the mean. Now we're looking at the interquartile range. This is basically, we're looking at the middle 50% of the data. And so that's from the 25th percentile to the 75th percentile, and that contains that middle 50%. There is an advantage to this. Because it's in the middle, it's not affected by outliers. So here's a tip. If you see the standard deviation and the IQR, the interquartile range, the authors are probably dealing with skewed data or outliers. So on this, we're trying to figure out how do we choose the right summary. We have to have a matching method to the data type. So if we have symmetric data, we can use the mean and standard deviation, and these use all data points efficiently. So that makes sense, right? It's symmetrical. Well, for skewed data, we have to use the median and interquartile range. And the reason we have to do this is because it's not influenced by extreme values. And it's more representative of the typical, or what some people might say normal patient, but we use the term typical patient. Now there's some red flags for using means. Obviously, there are some skewed distributions. We could be looking at your hospital length of stay. Most of them are short, only a few are very long. The time to recovery, the income data, all of those are skewed distributions. We also would have to look at a presence of outliers. So this is like the lab values with equipment errors, a data entry mistake. Then we also have like a real world example. If we look at the United Kingdom income data, the mean annual pay is equivalent to the 68th percentile. So this means 68% of people earn less than average. And this happens because high earners pull the mean upward. So the median gives us a better sense of understanding what a typical person earns. And our textbook says if the distribution is symmetric, then the mean and median will be close. As the distribution is skewed, then the mean and interquartile range are, in general, more appropriate summary measures than the mean and standard deviation. So when we're talking about displaying continuous data, we really should look at this from a pictorial standpoint because a picture is going to really show a lot more. We're looking at dot plots. We could show every individual's data point. This gives us complete information, so it's extremely easy for us to look at outliers. However, it does have a disadvantage because it can be very cluttered with large data sets. Well, if we look at histograms, this is group data in bins or intervals is what we discuss, and it will show our shape of our distribution. One of the things about this is that it can show the slightly right skewed, slightly left skewed. It actually can show you those types of distribution. Now, when we have box and whisker plots, this is not used as much, but it's literally a compact summary of 5 numbers. It's the minimum, it's the medium, it's the maximum, it's Q1 and Q3. And so within the box is going to be your IQR, your middle 50% of the data. The whiskers extend to all of the extreme outliers, as well as the additional data from the 25th to the out. And if you look at that, I think that makes a lot of sense. It's really great for comparing multiple groups side by side. And here's the thing, different plots reveal different aspects of your data. So you should always create multiple visualizations to help you fully understand your data and help others that you present to in understanding your data. So I always think that these, the skewed, the normal distribution, the positive skew always makes sense. When you show it to students, it tends to really cement the information within their brain. So we're looking at the mean versus the median and the mode. We have the bell-shaped curve, which of course we call a normal distribution, and it is the most common. The standard deviation is the most meaningful. Well, we look at height, weight within the same age, sex. We look at values. They're usually within that. The mean is the same number as the median and the mode when we're talking about a normal distribution. Now, if we have a right skewed or a positive distribution, one of the things that we see is the long tail to the right. So the mean is actually greater or further to the right than the median and the mode. And then you can see that the outliers are at the tail end of the distribution. Again, also we have left skewed, same exact thing, just a mirrored opposite. Long tail to the left, the mean is less than the median. So these are skewed data examples. What this means is they're skewed. You're looking, this is very common. Skewness is extremely common in medical data. You could look at hospital length of stay, time to recovery, income, and test scores, age at death. A lot of the shape of your distribution determines which summary statistics to use and which statistical tests are appropriate. So our textbook notes this. One important reason for producing dot plots and histograms is to get some idea of the shape of the distribution of the data. So we also have this within subject variability, and so this is when measures vary within the same person. A lot of studies only measure each person once, but let's say we're measuring the same person repeatedly and we see variation. So this is considered a within subject variation. It's distinct from between subject variation. So let's talk about, I wear a Fitbit. I know many of us do. Let's look at our step count example. So we have one person that measured for 100 days, and they had a mean of 14,107 steps per day. They had a standard deviation of 4,959 step variation. That's the within subject. And so their range was from 5,000 to 35,000 steps per day. And so now you see that their average, their mean within that is 14,107 steps a day. Well, why does this matter? Because there are biological variations, there's daily fluctuations in activity. If I'm in my office and I'm working on my computer and I'm creating PowerPoints for you and I am grading papers, what do you think my chances are of my steps being high? Obviously, they're not. But if I'm actively involved in teaching a class and I'm having to walk around campus, I'm having to go up and down steps because the elevator is broken. I'm having to walk across campus to the other side of the street from my office, which is on the third floor. There's going to be a daily fluctuation in activity based basically on what I'm doing. Well, we also have this whole idea of measurement error from true differences. What if we have a difficulty in our device? Maybe it's not our Fitbit, but maybe we're looking at even a blood pressure machine. What does this actually mean? Well, it could be you've got to look at this concerning, is there a device accuracy? Is the placement correct? Is it not? Um, but all of this distinguishes measurement error from true differences. Okay, so in our study design, we actually need enough measurements to get reliable estimations. Our clinical interpretation must be, is this a real change or is this just normal variation? So if I go into the doctor's office and I have white coat syndrome, should you take it after we've sat there for a few minutes? Sure. Why? Why would you do that? You can answer your question. You know this. What about sample size? More variable measures need larger sample sizes. And from our textbook, the experimenter must be aware of possible sources which contribute to the variation, decide which are of importance in the intended study, and design the study appropriately. Okay, so here we're looking at our presentation principles. And so when you're presenting your data, you want to make the data clear and you want to be honest. Well, this just kind of tells you what you need to do as far as making this happen. So you have to have clear descriptive titles. You have to have your axes labeled with the appropriate scales. You have to avoid a break-in scale. You have to use consistent scales for comparison. What if you have a table? Well, it's the same thing. You have to include counts and percentages. You have to use consistent formatting. A lot of things that are common mistakes would be misleading scales. So those are, making small differences look huge. We've seen this in other presentations and even just in our newspapers or on the news. If you have too much information, it's information overload. It's too much in one display. It's okay to have no words and white space. What about a wrong chart type? It's inappropriate chart type for the data. Well, a pie chart with 12 categories doesn't really show you. It's very misleading. It's very, why would you want to do 12 categories like that? You probably would rather have a table. So one of the ideas from the textbook says a graph should never include too much clutter. For example, many overlapping groups, each with a different symbol. So consider how you would want your data to look and be presented. So this is about critical reading checklists. These are things that you need to look at when reading medical literature. What about the data? Is the sample size clearly stated? Are appropriate summary statistics used? For skewed data, are the median and the IQR reported? Yeah, if you don't see that, that's a red flag, right? Are the axes clearly labeled? Sometimes this is missing in journals and it's extremely confusing. What about the scales? Are the scales appropriate? Have the questions also been asked appropriately? Is the graph suitable? We already know a pie chart for continuous data is wrong. Can you assess the distribution? So there should be enough information provided within the article that will tell you. And what about within subject studies? Is the variability addressed? And these are, when we look at critical at repeated measures, this is critical. Are they independent or is it correlational? So we have some red flags in literature, and that would be if there's a mean without standard deviation or a confidence interval, percentages without sample sizes, graphs with no scale or unlabeled axes, inappropriate statistical tests for the data. So one of the things that you want to look at is you need to develop a habit of looking at these items automatically when you read papers. So poor data representation also may signal a poor analysis of the data. Okay, so let's look at what does this mean? Well, I mean, we've got to figure out what do we do within the real world. Okay, so within clinical practice, how does this work? Well, we have lab reference ranges, and this means, it's usually based on the mean plus or minus student standard deviations from healthy populations. What about patient monitoring? Well, we have to understand this concept of normal variation versus concerning changes. In treatment evaluation, the treatment effects must be distinguished from natural variation. What about in research? Well, our proper data description aids the interpretation and informs our sample size calculations. If we have our data type determines our appropriate statistical test. We also have to understand the variability affecting clinical significance. And within our communication for patient education, clear presentations help patients understand their condition. Let me also say that one thing is a lot of times medical literature has to be lowered in reading ability. So make sure that your presentation is between a 5th and 6th grade level. When you are giving patient education information, we have to consider who our population is. We have to consider the variability of patient education and their ability to understand what we are telling them. And I'm going to give you a very clear concept of this. My father had a college degree, but it was from a private school way back in the 1940s and 50s. Basically, during that time, if you could send your child to college, it meant you had money. Teaching colleges and small colleges were often that were private were often used in that way. It's not as much today, which I think is really important, but back then. So my dad, while he could read, could not understand a lot of what the doctors told him. They did not know how to break it down. That is extremely important. So when you tell someone that they have non-alcoholic fatty liver disease, and they laugh because they go, well, I'm not an alcoholic, and his parents both had severe diabetes. One was type 1, one was type 2. We always suspected dad had diabetes but was misdiagnosed. And so when they told him to get on a certain diet, he just laughed and said, well, I'm not an alcoholic, so I'm okay. He didn't understand the non-alcoholic construct, that it could also have been a genetic issue. And so he died, while he died in his late 80s, he died from having non-alcoholic fatty liver disease that actually really had at that point brought on dementia, and he broke his hip. And so when we do not have communication uh, to our patients, they continue to eat sweets and not understand how to properly care for themselves. They're not given information. They're not given the decision making ability because they don't understand the words or the consequences or what we are saying to them. This is extremely important. So it's not just about having publications. This literally is working with patients and trying to explain to them how this can help them. This also means that we have to understand their individual um, lab references. And so that's a whole nother aspect of this. I think we have to really use this within our clinical work to make sure that people understand what we are telling them. So when we look at technology and tools for data analysis and presentation, and you guys will not be doing SPSS or Excel in here, mainly we want you to understand this because we want you to be able to read journal articles and interpret it. The statistical software is great. It does an automatic calculation of your summary statistics. It's an easy generation of multiple graphs. You can explore the data interactively. It's really great. Some of the good ones are SPSS data, SAS, R, Python. A very basic would be Excel. One of the advantages is that you can explore different presentations. You have consistent formatting and the complex calculations that my age group had to make on Texas Instrument calculators. We can do this much quicker. Now, here's the thing. The software cannot choose your appropriate method for you. Okay, it's also easy to generate misleading displays. We've already mentioned this, and understanding the principles still is highly essential. One of the biggest things is if we put garbage in to our software, we get garbage out, and SPSS cannot fix bad data. Another thing is it's extremely easy for us to mislead people by generating inappropriate analysis quickly. And, one of our best practice concepts is use technology to implement good statistical thinking, not to replace it. The computer should always be your assistant, not your decision maker. One of the key things is to learn the principles first and then use the software. This is one of the reasons why we don't use software in teaching right now. If you go on to graduate school, they will teach you SPSS or Excel or Stata or SAS or R. So, just be ready for something like that. But this should give you a good background. So what we want to talk about now is the misconceptions and how do we avoid the statistical traps. Well, the mean is always the best. Okay, that's incorrect. That's wrong for skewed data or small samples with outliers. A bigger sample equals more accuracy. Yeah, no, because within subject variability still matters. And the quality of the measure matters more than the quantity. This is really more important. Pie charts are always clear. Pie charts are good for comparisons. Bar charts are good for comparisons. Pie charts are not good for every category. Okay. Standard deviation tells you about normality. Well, standard deviation is about spread and not shape. And so that could be used for misleading skewed data. When these misperceptions are very common, even among researchers, you need to be aware of them, and that makes you a more critical consumer as well as a producer of statistical analysis. Using real data, um, data gets complicated. Real data is messy. So, if we look at the foot corn study, it had some missing values for measurements. How do you handle that? Sometimes you'll see impossible values, negative ages, 200% response rate, that are clearly errors. Developing judgment about these situations comes with experience, but what you've learned provides the foundation. Well, when we talk about, the missing data, how do we handle incomplete information? When do we exclude versus estimate missing values? How do we do this? Well, we have to also report how missing data was handled. What about extreme values? There's some outliers from data entry. When do we include versus exclude unusual observations? Well, let's talk about what's a data entry error. We might see a 200-year-old patient. Yeah, that's not happening. Or a negative weight. That's not happening either. What about true outlier? So there's a 95-year-old marathon runner, right? That's an outlier. A rare disease presentation. That's an outlier. So first we have to investigate, and then we have to decide on how we're going to handle it. What about multiple groups? Which groups to compare? How many comparisons? And choosing the appropriate comparison. And we also have to not use information overload. Sometimes we fail to consider too many categories in one display. So what is our solution? Well, we should focus on clinically meaningful comparisons. Longitudinal data, repeated measures, it's the same person measured multiple times. We understand within and between subject variation with longitudinal data. Real data is messy. Okay, let's just be real. It's messy. The challenges require judgment, not just technical skills. And so, as someone who works with statistics, this is the problem, is it's your judgment. It's not, can I do the work? It's, do I understand what I need to present, or how am I going to get this information put into a graph or a presentation? These 7 principles will guide you through most data presentation challenges. So when in doubt, think about what story your data is telling and how best to communicate that story to your audience. Good statistics is ultimately about clear conversation and communication. So go through each point systematically here. So our data type determines our method. Well, this is a fundamental principle of data. We have to match our statistical approach to data characteristics. Both location and spread matter. Your mean without your standard deviation is incomplete information. So your central tendency alone is not enough. What about visualizing your data? Graphs reveal patterns and numbers cannot. Graphs reveal these patterns that numbers alone cannot do. We also have to choose appropriate summaries. We have to match the method to the data characteristics. So we have to use mean and standard deviation for symmetrical data and the median IQR for skewed data. What about variability? Our within subject variation affects our interpretation of the data. Our audience should easily understand our data. We have to present our data clearly. And then we have to also question our statistical choices within literature. We have to read critically. We also have to reinforce the idea that all of these takeaways, these are not separate topics. They're interconnected principles that work together to help you understand and communicate about your data effectively. So, what is the best way to master these concepts? Well, start noticing how data is presented in papers you read. Try creating different summaries of the same data to see how presentation affects interpretation. So, these skills will help you through your career in healthcare and in research. One of the key things is to remember understanding principles matters more than memorizing formulas. You can look those up. You can calculate those out. You can Google them. But the principles are more important in how we uh, apply our data, how we critically evaluate it, and the presentations and publications in medical journals, and all of, we have to look at what is good and poor data presentation. So today we've covered the foundation of statistical analysis, understanding and describing data. Next chapter we'll build on this foundation to learn about probability and making inferences from samples to population. So the concepts we've learned today, understanding data types, choosing appropriate summaries, presenting data clearly, will be essential for every single thing that follows.